G'day and welcome. This video is part 3 in a series of videos dedicated to the elimination of fuel surge in the Toyota 86 and Subaru BRZ without spending a fortune. Details are next. I'm Mark Louth from Black Dog Motorsport, and if you or someone you know has the black dog chasing them, there are some links in the description that you may find useful. Parts 1 and 2 of this series dealt with finding out how the fuel pump operates using a custom-built test fixture. Now, if you haven't seen parts 1 and 2, I would recommend that you do so. There is a link in the description, or you can click on the card in the top right of the screen. Now, if you haven't, that's okay. I'll quickly catch you up. I am attempting to install a second fuel pump on the other side of the fuel tank, so regardless of the lateral loading and fuel level, one pump will always have its pickup submerged in fuel, therefore eliminating fuel starvation. Now, the fuel system in the twins is a deadhead system, which means there is no fuel regulator at or near the fuel rail, and as a result there is no return line to the fuel tank. There is a fuel pressure regulator integral to the fuel pump, but it is a maximum pressure blow-off type only. Therefore, if the ECU requires a change in pressure, it alters the voltage supplied to the fuel pump. It is therefore important that any second fuel pump reacts in exactly the same way as the OEM pump, and equally importantly, the second pump must be invisible to the ECU. This is to ensure that the ECU sees the expected change in pressure when it alters the voltage to the fuel pump, and it does not see the power drawn by the second fuel pump. If either of these things do happen, then there is a better than even chance the ECU will throw a fault code. Okay, so now that everybody is on the same page, let's get on with it. What you're looking at here is a circuit diagram for a fuel pump control module I have designed to achieve the aforementioned criteria. Now, I'm not going into an in-depth discussion on how it works, however I will give a brief overview. The circuit consists of 3 parts. The first is just a straight through section. This consists of a circuit for the OEM fuel pump and both of the OEM fuel senders to pass straight through the control module from the inlet plug to the outlet plug without any interruption, and to not affect the operation of either. The only reason for including these items was to keep the installation neat and tidy with one plug in and one plug out, rather than splicing a control model into the middle of the loom. And secondly, and more importantly, our second fuel pump control system must have access to the power supplied to the OEM pump so it can mimic it. The second section is in this module is the voltage follower section, and as the name suggests, the voltage at this section's outputs directly matches the voltage at its input. And if we follow this line here, you can see the input is connected directly to the positive power supplied to the OEM pump. So if there is a change to the voltage supplied to the OEM pump, the output of the voltage follower will change to match it. It is also important to note here that the input to this section is a very high impedance, which put simply means the primary circuit cannot see the secondary circuit, which is exactly what we want. The component that achieves this little piece of voodoo magic is this little fella here, which is a general purpose operational amplifier costing around $5 at an electronics store near you. Now, if this component mimics the voltage and is invisible to the primary circuit and therefore the ECU, you could be forgiven for thinking that that's job done and no other circuits are required. Unfortunately, you would be, like I was, wrong, because like everything, the devil is in the detail. Now, during testing we saw the pump draws up to 5 amps of current, and that's a bit of an issue. Our little $5 op amp would turn itself into a charcoal briquette in very short order if we tried to pump 5 amps through it. Now, while you can purchase operational amplifiers that can handle 5 amps or more, they start at around $250 US each and go up from there. So, that ain't gonna happen. Therefore, we need this section here, which is a current buffer. In the current buffer section, the voodoo magic is performed by this component here, which is called a MOSFET. And it's going to, hopefully, perform 2 functions. 1, work as a variable resistor, and 2, work as a straight through path for the supply voltage to the second pump. How does it do that? Let's have a very quick look. MOSFET stands for Metal Oxide Semiconductor Field Effect Transistor. Now, most people have heard of the term transistor before, I'm sure. However, when you do hear that term, generally speaking, it is referring to what is known as a BJT, or bipolar junction transistor. These transistors were originally made from germanium, but are now almost exclusively made from silicon. Both the BJT and the MOSFET are semiconductors, but unlike the BJT, the MOSFET is made primarily of metal oxide, which gives us some very desirable characteristics for our application. Namely, unlike a BJT, which in most cases is either on or off, a MOSFET has a range between fully off and fully on, which means if we can operate in that range, we can vary the voltage that flows through it, just like the op-amp is doing in the voltage follower section. The difference being the MOSFET I'm using here can handle up to 30 amps, which is more than enough to run our second pump, hence the term current buffer. The MOSFET literally buffers the op-amp from the high current supplied to the second pump. So anyway, that's the theory, and it literally is just that, theory. The only way to find out if it works is to build it and then test it. So let's do that. Using the power of video editing, here is our completed prototype. The circuit board is better than I expected. However, looking at the real thing in my hand as opposed to symbols on a computer screen, I'm already rethinking the choice of header pins, as I don't think the normal size wire that fits these kinds of plugs is going to be able to handle the 5 amps of continuous current. But anyway, let's test it and find out for sure. Okay, here is our prototype on the bench, wired up through a breadboard to two power supplies. Now, one is mimicking the supply voltage to the OEM pump, and the other is taking the place of a direct power feed from the battery for our second pump. I've also hooked up some multimeters to measure our outputs, and I have a couple of 1 megohm resistors hooked up in place of the pumps to supply a dummy load to the circuit. So let's turn it all on and see what we get. And what do we get, ladies and gentlemen? A big fat nothing. Donk donk. And why did we get a big fat nothing, ladies and gentlemen? That's because I am an idiot who cannot read a data sheet for an electrical component, or so it would seem. When I went back and had a look at the data sheet properly for the operational amplifier, I found out that it has an inverted output, which means the voltage at its output will be the inverse of the voltage at its input, which means it won't work. So I've got to get a new one and we'll try again. Well, that's about it because I've had enough. So until next time, I'll see you later. Bye for now.